Hello everyone, welcome to the NPTEL live session 2. In the last session, we talked about, we solved some problems regarding shallow foundations. Mm, In those cases, the shallow foundation was resting on flat ground surfaces. But today, we are going to discuss some problems related to shallow foundations. So today we are going to discuss some problems related to shallow foundations, but in today's cases, the shallow foundations are resting on top of a slope maybe, or maybe they have a tilted base, or maybe they are resting on a layered soil. Okay, so my name is sinjandebnath. I am a PhD student in the Department of Civil Engineering at IIT Kharagpur, and I welcome you to this session. So let's go to the first problem. Can you please let me know if you can hear me or not? Am I audible? And can you see the slides? Please, someone let me know, please. Hello, can any of you please let me know if I'm audible or not? Hello, hello, am I audible? You can also reply in the chat box. Please let me know if I'm audible or not. Hello, can you hear me? Am I audible? Please let me know. Please let me know if I'm audible or not. You can also type in the chat box. Okay, I guess I'm audible, so I'm starting. So let's come to the first question. So what it is saying? According to Hansen's theory, determine the ultimate bearing capacity of a strip footing of width 3 meter resting on a top of a slope such that the embedment depth is 0. The slope is making an angle of 15 degrees with the horizontal. So let me draw it first. So a strip footing of 3 meter. So this is a strip footing of width 3 meters. It is resting. It is a strip footing of 3 meter. It is resting on top of a slope such that the embedment depth is 0. So that means it is resting on top of a slope like this. df is equal to 0. The slope is making an angle of 15 degrees with the horizontal. That means this angle, beta. is equal to 15 degrees. The friction angle of the soil is 40 degrees. The friction angle of the soil is 40 degrees. C value is 0. The corresponding bearing capacity factors NQ and N gamma are 64.1 and N gamma is equal to 79.5 respectively. The load is acting vertically at the center of the footing. That means load is acting vertically. There is no horizontal load, and there is no that is why there will be no inclination factor. The load is acting vertically. Soil compressibility and water table effects are neglected. The foundation base is not tilted. The unit weight of the soil is 18 kilonewton per meter cube. That means gamma is equal to 18 kilonewton per meter cube. So now let's solve this problem. Now it is mentioned in the question that the load is acting vertically at the center of the footing. So there will be no inclination factor. Soil compressibility and water table effects are neglected. So water table correction and compressibility, that is CC, compressibility factors like CC, C gamma and CQ, all those factors are not needed. The foundation base is not tilted. That means the base factors are also not needed. The base factors means BC, BQ, B gamma. These are also not needed. The only correction here it is needed is the sloping correction, the slope ground correction, the sloping ground correction, sloping ground factor. Okay. So let's get started. So what is the bearing capacity? So here we are asked to determine the ultimate bearing capacity of a strip footing. So what is the formula for the ultimate bearing capacity? QU is equal to CNC into shape factor, depth factor, CNC into shape factor, depth factor, inclination factor, compressibility factor, sloping ground factor, and the tilt base factor. And the rest two terms are also like this: Q, NQ, and all the factors SQ, DQ, IQ, CQ, GQ, and BQ. And the third term is half into gamma B in gamma and all the corrections, that is that all the corrections, all the factors like shape factor, depth factor, inclination factor, compressibility factor, sloping ground factor, and base factor. So this is resting on the ground. The footing is resting on top of a slope. That means df is equal to 0, and also it is a completely cohesionless cell. That means c is equal to 0. So c is equal to 0. That means this part will be 0 since c is equal to 0. And since it is resting on top of a slope, this q, what is q? Q means gamma into df. So df is equal to 0. That means this part will also be 0. So ultimate bearing capacity will only be this part. So now we need not uh, consider all the factors, because you see in the question it is already mentioned to not to consider compressibility effect, and also it is said here that the base is not tilted and also the load is acting vertically. So there will be no inclination factor, there will be no compressibility factor, and the base is also not tilted. So there will be no base correction factor. Okay. So now QU is equal to half into gamma B n gamma S gamma D gamma and G gamma. So we know the unit weight of the soil, we know the breadth of the foundation, we know the value of n gamma. So for strip footing, this is a strip footing. For strip footing, S gamma is equal to 1. D gamma is also equal to 1. And G gamma. So we know this, we also know this and this, only G gamma. So G gamma, this sloping ground factor, we have been asked to find out the ultimate bearing capacity of this footing using Hansen's theory. So according to Hansen's theory, if we look at this chart, according to Hansen's theory, this one, the GQ equal to G gamma is equal to 1 minus 0.5 tan beta to the power 5. This factor we need to use. Okay. So G gamma is equal to 1 minus 0.5 tan of beta degree to the power 5. Okay. So 1 minus 0.5 tan of beta. So what is beta? Beta is the sloping angle, which is 15 degree in this case. So 15 degrees to the power 5. Now if we solve this, we will get this 0.487. This is the value of the sloping ground factor. So now we know the values of all the parameters. We know the unit weight, we know the breadth of the footing, we know the bearing capacity factor n gamma, we know the shape factor, we know the depth factor, we know the sloping ground factor. So now if we put all the value of all these parameters into this equation, so now if we now put all the values of all the parameters into this equation, that is equation number 1, we will get the ultimate bearing capacity. So let me write the equation once again. QU is equal to half into gamma B n gamma, shape factor, depth factor and sloping ground factor. Shape factor, depth factor and sloping ground factor. So what are the values of all these parameters? The unit weight of the soil is, so what is the unit weight of this soil? It is 18 kilonewton per meter cube. So it is 18. And what is the width of this footing, of this strip footing? It is 3 meter. 3. And what is the value of n gamma? N gamma is 79.5. And shape factor, depth factor is 1. For strip footing, shape and depth factor is 1. These are 1. The shape factor, the third shape factor for the third term, 1 into 1. and the sloping ground factor which you have calculated, it is 0.487, and this comes out to be 1045.35 kilonewton per meter square. You guys also please calculate this equation and let me know if I have done any calculation mistake. Uh, Please solve all the problems along with me, okay? Because in this way you will learn very easily. So if you have any doubts, you can ask me now. If you have any doubts in this particular question, you may ask me, or else I will go to the next question. If you have any doubt, please let me know. Okay, so let's come to the second problem. So in this problem, according to basics theory, so we need to use the basics theory in this case. Determine the ultimate bearing capacity of a strip footing of width 3 meter placed at a depth 1 meter below the ground surface. The foundation base is tilted by an angle of 12 degrees with the horizontal. So in this case, the foundation is tilted. The friction angle of the soil is 40 degrees. C value is 0, that means it is a cohesionless soil. The bearing capacity factors, that is NQ and N gamma, are given over here. NQ is 64.1, N gamma is 109.4. The load is acting at the center of the footing and perpendicular to the direction of the footing. That means no horizontal forces are acting over here, so we don't need the inclination factors. Soil compressibility and water table effects are neglected, so we also don't need to incorporate the compressibility factors and water table effects. The unit height of the soil is 18 kilonewton per meter cube. So let me write down the data which are given over here. So first let me draw the picture. The foundation base is tilted by an angle of 12 degrees the horizontal. The width is 3 meter and it is placed at a depth of 1 meter below the ground surface. Okay, fine. So suppose this is a ground surface and the foundation base is tilted like this. Suppose this is the depth of the footing is 1 meter below the ground surface and the width of the footing is 3 meter in this case, and the foundation is tilted by an angle of 12 degrees. So that means this particular angle I am representing it by eta. It is 12 degrees with the horizontal. The friction angle of the soil is 40 degrees and C value is 0. The corresponding bearing capacity factors for 40-degree frictional angle is NQ is 64.1 and N gamma is equal to 109.4, and the load is acting at the center of the footing. Okay, so that means there is a load at the center of the footing and perpendicular to the direction of the footing. So that means there is no need to incorporate the inclination factors. Soil compressibility and the water table effects are neglected. So gamma is equal to, and the unit weight of the soil is 18 kilonewton per meter cube. So the unit weight of the soil is 18 kilonewton per meter cube. So now let's solve this problem. Since the foundation base is tilted in this case, we need to incorporate the tilted base factor. So first of all, so we have been asked to find out the ultimate bearing capacity of this strip footing using basics theory. So let me write down the formula for the ultimate bearing capacity, QU. Since this is a cohesionless soil, so that means C is 0, and that's why the first term, that is the CNC and the shape factor, CNC multiplied by shape factor, depth factor, all those things are 0, because the first term is 0 because C is equal to 0, right? So only the second term and third term will be present, because the second term will also be present because the depth is 1 meter, I believe. The depth of the footing is 1 meter. So the second term will also be present over here. So let me write down the second and third term. Gamma df in q, sq, dq, iq, cq, bq, gq plus half into bn gamma, s gamma, d gamma, I gamma, c gamma, b gamma, and c gamma. There is no need to incorporate this sloping ground factor because there is no slope, only tilt. So only BQ will be there, and only the B term will be there. Over here also only B term will be there. This will not be there. Compressibility, soil compressibility is, and it has been asked over here not to consider the soil compressibility. So that means CQ and C gamma will also not be there. Okay. So for strip footing, since this is a strip footing, for strip footing, SQ is equal to S gamma is equal to 1, and the depth factor, okay, the depth factor dq. So we need to find out the and also the load is acting vertical. So that means the inclination factor will also not be there because the load is not inclined. So now we need to find out only SQ, DQ, and BQ. Only S, D, B. Only S factor, only this, and this. Only three factors are needed. SQ, DQ, BQ in for the second term, and for the third term, S gamma, D gamma, and B gamma. Okay. So SQ and S gamma is equal to 1 for the strip footing. But DQ, this DQ is equal to, first of all we need to this DQ is equal to, for basics we need to find this ultimate bearing capacity using basics theory. So for basics theory, DQ is equal to 1 plus 2 tan phi 1 minus sin phi square into K. You can find this in any textbook, and you can also find this in the lecture of advanced foundation engineering. So now this value of K, okay, what is K? This K is a, this K is a coefficient which we need to find out. So first, in order to find out the value of K, we need to find out the ratio df by b. So what is df by b in this case? If df by b, if df by b is less than 1, then K value is df by b. But if df by b is greater than 1, in that case K value is equal to tan inverse df by b. Okay, so first of all we need to find out the value of df by b in this case. So what is df by b? df is equal to 1 meter, the embedment depth 1 meter, and the breadth of the footing is 3 meter. So df by b is 1 by 3. So it is less than 1 meter. So it is less than 1. So it is less than 1, that means k is equal to df by b. That means k is equal to df by b, which is equal to 1 by 3. So now let's find out the value of dq. Okay, so dq is equal to 1 plus 2 into this 1 plus 2 into tan phi 1 minus sin phi square into k, this one. So 1 plus 2 into tan of 40 degrees 1 minus sine of 40 degrees square into 1 by 3. Now if we solve this, we will get dk is equal to 1.07. And for strip footing, d gamma, then another factor, depth factor for the third term, it is 1. Okay, so do we have all the factors? We have sq, we have dq, we have now, but we don't have bq. That is the that is the base tilt factor, tilt base factor. So we need to find. We also have s gamma, d gamma. So we need to find out the tilt base factor, that is the bq and b gamma. So bq and b gamma for basics theory. So here if you look at this chart, for basics theory, bq is equal to b gamma, this one. bq is equal to b gamma, which is equal to 1 minus eta, that is the tilt base angle, that is the angle the base of the foundation is making with the horizontal ground, that is 1 minus eta tan phi square, and eta obviously is in radians. So let me write it down over here. bq is equal to b gamma, it is 1 minus eta tan phi square, equal to 1 minus eta into tan phi square. This one is in degrees and this one is obviously is in radians, eta. So now let's find it out. 1 minus eta. So what is the angle the foundation base is making with the horizontal? It is 12 degrees. So eta is 12 degrees and this one is in radians. So that means pi by 180 degrees. I am converting 12 degrees into radians. Okay. So now this one multiplied by tan phi. Tan, what is the value of frictional angle of the soil? It is 40 degrees. So tan of 40 degrees square. So if you calculate this, you will get bq equal to b gamma is equal to 0.68. So now I believe we have the values of all the parameters. We have sq, dq, bq, s gamma, D gamma and B gamma. So now let us put all the values of all the parameter into this equation number 1. So what is QU? QU is equal to gamma DF NQ, gamma DF NQ, SQ, DQ and BQ, SQ, DQ and BQ, plus half into B and gamma, S gamma, D gamma and B gamma. Inclination factors, compressibility factors and the sloping factors are not included. S gamma, D gamma and B gamma. So now let us put all the values of all the factors in this equation. What is gamma? What is the unit weight of the soil? It is 18 kilonewton per meter cube. So 18. What is the embedment depth of the footing? It is 1 meter. What is the value of NQ? The value of NQ is 64.1. The value of NQ is 64.1. And what is the value of SQ DQ? The sloping factor for strip footing, the SQ and S gamma is equal to 1. Okay, so SQ is equal to 1. And what is the value of DQ in this case? The DQ we calculated, the DQ is 1.07. Okay, so DQ is equal to 1.07. And what is the tilt base factor? That is BQ. The BQ is equal to B gamma, which we calculated. It comes out to be 0.68, 0.68. So 0.68 plus the third term. So half into base. What is the width of the footing? It is 3 meter. So half into 3 meter into what is the value of N gamma? N gamma is 109.4. So 109.4 into what is the value of S gamma? S gamma is equal to 1 for strip footing. So S gamma is 1. What is the value of D gamma? D gamma is 1 for strip footing. For basics theory, in case of strip footing, D gamma is equal to 1. So D gamma is equal to 1. And what is the value of B gamma? B gamma is equal to BQ is equal to 0.68, which we calculated. So it is 0.68. Now if we calculate this equation, we will get, if we multiply these terms and add them together, we will get QU is equal to 2848.1 kilonewton per meter square. You are asked to solve this problem. Please solve this problem so that we can verify whether I have done any calculation mistake or not. Okay, so that's why I'm asking you to solve all the problems along with me. You will also get a better understanding. Okay, so if you have any doubts, you can tell me now. So if you have any doubt regarding this tilt base problem, the problem in which the foundation base is tilted, you can just tell me now. If you have any doubt regarding this calculation process, you may tell me now. Guys, if you have any doubts, please tell me, or else I will proceed to the next problem.
Okay, sir.
Okay, sir. Okay, so everything is clear. Okay, everything is clear in this problem. So let's go to the third problem. So the third one. Now the next few problems, problem number 3, 4, 5, and 6, are are based on this method, Mayor of 1924 and Mayor of and Hannah 1978 approach. We This is a single approach actually. It was developed by Mayor of initially, and later the approach was modified by both Mayor of and Hannah. In this approach, when we use this approach, in this approach actually the shallow foundation is founded upon a layered soil. That means two layers are there, one above another, and on the top layer the foundation is founded. And in order to find out the bearing ultimate bearing capacity or bearing capacity for the whole system, that is the two layered system, we use this approach. So you will find this approach in the lecture, in the week 4 lecture, and I will also show you how to solve using this approach. This is a single approach, Mayor of 1924 and Mayor of and Hannah 1978 approach. This is a single approach. So first of all, let me brief about this approach. Let me show you how to calculate using this approach. Later on, I will solve this sum. Okay. Suppose you have a footing. You have a footing at the embedment depth of the footing is df. So let me draw the footing first. Suppose this one is your footing. This is the depth df is equal to 1 meter. So now you are applying load over here q. So and the footing is founded on this soil, and there is another soil below this soil. Okay, let us consider the top soil. This one is a stiffer soil, and the lower one is a softer soil. Okay, so stiffer, so the all the parameters are like gamma 1 and phi 1 and the c1. These are all the properties of this of the top layer. And for the softer layer, the properties are let it be gamma 2, phi 2, and c2. Okay, so now this the foundation depth is df, and this depth, the depth between the base of the foundation up to the end of the top layer or the starting of the second layer. So this depth is termed as h. Okay, so now h. So in this case, if this value of h is not large enough, that means if the top layer, the thickness of this layer is such that it is not large enough, in that case, at ultimate bearing capacity, that means if you increase the load and at the ultimate point, the soil will feel like the failure surface uh, below the footing will be like this. You have studied the general shear failure patterns and the local shear failure patterns. Okay, for only a single homogeneous soil layer, but here there are two layers, one above another. So in that case, if the depth of the top layer is not large enough, so in that case the failure will be like this. The failure surface will move from the first layer to the second layer, and it will develop like this. It will develop like this. Okay, so that is why in these cases, in the layered soil cases, we need to find out The ultimate bearing capacity of this whole system include we need to incorporate both the first the top layer and the layer below the top layer, okay, the second layer. I hope you have all understood the situation. This is the situation. So what is the formula for this case to incorporate both the layers for the two layered system? So for the two layered system, so for the two layered system, the ultimate bearing capacity of the footing Qu is given by Qb plus 2CAH. I will explain all the terms. Let me write it first. 2CAH by B plus gamma 1 into H square 1 plus 2 df by H. So as I was writing, so for two layered system, the ultimate bearing capacity is given by QB plus 2CAH by B plus gamma 1 into H square into 1 plus 2 df by H into Ks tan phi 1 by B minus gamma 1H. I will explain all the terms. Okay. So what is happening in this case? So please refer to this picture. So what is happening over here? I am telling you once again. There are two layers. The first one is stiffer layer, and below the stiffer layer there is a softer layer. And on the stiffer layer, our foundation is founded at a depth of 1 meter. Okay. So this depth, the depth of the top layer is such that the failure surfaces are transferring. The failure surfaces are moving from the top soil to the soil below it. Okay, from the stiffer soil to the softer soil. Because if the value of if the soil layer is such that this value of H is such that it is very low, suppose it is very low, so in that case at ultimate state, if you load the foundation to its ultimate state, that is if you apply the load near to its ultimate bearing capacity, or if you apply similar ultimate bearing capacity on the foundation, the strip footing, then the failure pattern will develop like this. It will move from the top layer to the layer underneath to the softer layer. So the failure surfaces will be like this. Now what is happening that the foundation is trying to move downwards like punching shear. Okay, so Mayor of what he did is that he assumed that the foundation is moving like this. Okay, foundation. So he assumed that foundation moved like this along this dotted line. It is punching. Okay, so this the adhesion along this line, along this zone, along the vertical shear plane. This is actually a vertical shear plane. This dotted line. So it is a hypothetical. It is theoretical totally. So along this dotted line, the adhesion coefficient is defined as Ca, which is a multiple of which suppose alpha into C. C is the cohesion of the top layer, that is C1. So alpha into C1. So Ca, it is like this. We know the gamma 1. Gamma 1 is the unit of the topsoil. H we know. H, what is H? H is this part. This part is H. The depth between the thickness between the base of the foundation and the end of the top layer. We know that the B is the width of the foundation. Gamma 1 is the unit of the top layer. H is H. We know what is H. What is H? So df is the depth of the foundation. Ks. Now what is Ks? Ks is the punching shear coefficient. Okay. Ks is the punching shear coefficient. There are curves from which you can find out the Ks. But since in from there you can find out the value of Ks, the value of Ks depends upon five values. Okay, five values and the bearing capacity ratios of the top layer and the second layer. And we know the value of B, we know gamma 1 and H. Okay, so and this QB, what is QB? QB is the bearing capacity of the bottom layer. So if we are asked, if we are asked to find out the bearing capacity, the ultimate bearing capacity of the two layered system, okay, for the two layered system, then we need to use this formula. Okay, in that case we need to use this equation. The next few questions, if you follow the next few questions, you will understand everything, because the information, the data is almost similar for the next three questions. The data are similar, but we need to determine three different things. In the first question, let me read out the first question. A rectangular footing of size 2 meter by 4 meter is founded at a depth of 1 meter in stiffer clay. Okay, so there is no phi. The thickness of the stiffer layer is 1.5 meter. The Let me draw it. So in the question it is saying that the size of the footing is 2 meter by 4 meter. So B is equal to 2 meter, L is equal to 4 meter, and it is founded at a depth of 1 meter in stiffer clay. So DF is equal to 1 meter. So let me draw it like this. This is a footing. The breadth of the footing is 2 meter. It is founded at a depth of 1 meter. So suppose this one is 1 meter. It is founded at a depth of 1 meter. The thickness in the stiffer clay, the thickness of the stiffer layer is 1.5 meter. So the thickness, suppose the layer, this is the layer, top layer, the whole thing up to this, the thickness, this is the stiffer layer. The thickness of the stiffer layer is 1.5 meter. So what is the value of H from this part to this part? It is 0.5. H is equal to 0.5 meter. The water table is at a depth of 0.5 meter from the ground level. So water table is over here. Point 0.5 meter from the ground level. GUWT, ground water table, is over here. A softer clay layer is located below the stiffer layer. So there is a softer layer. So a softer layer is okay. So a softer clay layer is located below the stiffer layer. The underend cohesion of the stiffer and the softer layer is 100 kPa and 35 kPa. So C1 is equal to 100 kPa, C2 is equal to 35 kPa respectively. The saturated unit weight of the stiffer and softer layer is 20 and 18 kilonewton per meter cube respectively. So gamma 1 is equal to 20 gamma sat sat 1. The the saturated unit weight of the stiffer and softer layer is 20 and 18 kilonewton per meter cube respectively. So gamma sat1 is equal to 20 kilonewton per meter cube and gamma sat2 is equal to 18 kilonewton per meter cube. And what are the other things? The unit weight of the stiffer layer above the water table is 18 kilonewton per meter cube. So the unit weight of this part, okay, above the water table is 18 kilonewton per meter cube. So now determine the bearing capacity of the bottom soil layer. Only the bottom soil layer, okay. We are asked to find out the bearing capacity only for this layer. So there is no need to consider both the soil layers. We will come to that in the after a question, okay. In the next question we are asked to, I believe we are asked in the next question we will be asked to find out the bearing capacity of the top layer. But in this question and the question after that, a question will come where we will need to find out the bearing capacity of the two layered system, okay, of the whole thing. So in this particular question we need to find out the bearing capacity of the bottom layer only for the softer layer. So what it is saying, determine the bearing capacity of the bottom layer QB. The unit weight of the water is 10 kilonewton per meter cube. Use Meyerhof and Hanna 1978 approach. And it is mentioned that vertical load is acting at the center of the foundation. That means inclination factor will be 1. There is no need to consider it. And neglect the soil compressibility effect. That means there is no need to consider the C factors like C gamma, CQ, all those factors. Okay. So now let us solve this problem. In this particular question, we are asked only to find out the ultimate bearing capacity, ultimate bearing capacity of the bottom layer only, that is QB. So what is the formula for QB? For QB, if you look in this equation, we need only this part, okay. We are asked to find only QB is the ultimate bearing capacity of the bottom part only for the bottom soil layer, only this. In this question we need to find out only this part. So QB, what is QB? QB is equal to C2. C2 means 2 stands for the second layer. C2 NC2 SC2 plus gamma 1 unit weight of the top layer. So what is the thickness of the top layer? It is df plus h, this df and h. So df plus h into nq to sq2. Okay. So this is the surcharge. Gamma into df plus h is the total surcharge acting on the top of the bottom layer. Okay. So what is the surcharge acting on top of the bottom layer? It is the unit weight. If we look over here, so what is the actually over here? This one, let me. These two diagrams are similar. Here, the failure surfaces are defined. I have defined the failure surfaces, and this in this data and this in this picture I have described all the data. So if we look at this picture, what is the surcharge acting on top of this bottom layer? What is the surcharge acting on top of this bottom layer? It is gamma, that is this part. If we consider top of the soil layer, the gamma, this one, the gamma, let it call, okay, only gamma means 18 kilonewton per meter cube. This into 0.5, 0.5 plus this portion. This portion is totally submerged. So we need to consider the submerged unit weight of this part. So gamma sub 1. And what is the height of this part total? Let it be gamma 1. Okay, this one is gamma 1. So what is the height of this part total? The height of this part is, if the top this part is zero point 0.5, then this part will be 0.5 and the value of h is 0.5. So that means it will be 1. Okay, so it will be like this. So this one is the surcharge that is acting on top of the bottom layer. Okay, so let me first write down the bearing capacity equation. Okay, this one is the bearing capacity equation. Now, for now now, if we look at both the layers are clear. That means both the layers are clear. That means phi is equal to 0. And for phi is equal to 0, and for phi is equal to 0, n gamma is equal to 0 and nq is equal to 1, right? So and nc is equal to 5.14. So that means if we incorporate all these factors into this equation, we'll get. Now let us put all the other parameters C2. So what is C2? C2 in this case is 35 kPa. So 35 multiplied by NC2. What is the NC2? NC2 is 5.14 for clay. And shape factor. This is a rectangular footing. So I need to include the shape factor. So what is the shape factor? It is 1 plus 0.2 B by L. Okay. Now surcharge. This is the surcharge Q value. So what is Q? We have calculated Q over here. This one. So what is Q? Surcharge acting on top of this layer. It is gamma 1 into 0.5. So what is gamma 1? Gamma 1 is equal to 18 kilonewton per meter cube. So 18 into 0.5 plus gamma saturated into this whole part. Okay, we have considered gamma 1 for this part, that is above the groundwater table. The unit weight is gamma 1 is equal to 18 kilonewton per meter cube, and below the groundwater table, all the soil is submerged. So for that we considered the submerged unit weight, that is gamma 1 dash. Okay, gamma 1 dash. So we know the gamma 1 the gamma saturated one, that is the 20 kilonewton per meter cube, the saturated unit weight of this part. So if we subtract the unit weight of water from that part, we will get the submerged unit weight. So and the thickness of this part is 1 meter below the groundwater table till up to the top of the second layer. It is the thickness is 1 meter. So the unit weight of the saturated unit weight is 20. So that means 20 minus 10 into 1. Okay, this is the value of Q. And what is the value of NQ? it is 1. And also the shape factor, that is the SQ2, it is also is equal to 1. So now if you solve, now you know the value of B. B is the width of the footing. How much is the width of the footing? B is equal to 2 meter, L is equal to 4 meter. This B is equal to 2 meter, L is equal to 4 meter. So now you know all the values of all the parameters. Now if you just calculate this equation, you will get 217 kilonewton per meter square. Okay, so this one is the ultimate bearing capacity of the second layer, of the softer layer. Okay, that is QB. We will need this while when we will calculate the bearing capacity of the two layered system. So in this equation, QB is this part. Okay, so guys, if you have any doubt regarding this question, you may ask me now. Have you all understood this problem? Please let me know if you have any doubt. Okay, I am giving you 5 minutes. Please let me know if you have any doubts. Please follow this question properly. If you have any doubts, please let me know.
No doubt, sir.
Okay, thank you. Then I am proceeding to the next question. See, in this question, the information is similar. Okay, the footing is similar, but here we have been asked to determine the bearing capacity of the top soil layer. Okay, in the last question, we are asked to determine the bearing capacity of the second layer, of the bottom layer. In this question, we have been asked to find out the bearing capacity of the top layer. Okay, and all the other informations are similar. Okay, so a rectangular let me read out the question once again. A rectangular footing of size 2 meter by 4 meter is founded at a depth of 1 meter in stiffer clay. The thickness of the stiffer layer is 1.5 meter. The water table is at a depth of 0.5 meter from the ground level. A softer clay layer is located below the stiffer layer. Let me draw it once again. This is a footing. The breadth is 2 meter. It is founded at a depth of 1 meter in stiffer clay. dF is equal to 1. The thickness of the stiffer layer is 1.5 meter. So this is the thickness of the stiffer layer. The water table is at a depth of 0.5 meter below the ground level. So suppose here it is. The depth of this part is point, like the previous problem. A softer clay layer is located below the stiffer layer. Please wait for a minute. So, as I was saying, this is a softer layer. So, a softer layer is located below the stiffer layer. The undent cohesion of the stiffer and softer layer. The undent cohesion of the stiffer and the C1 cohesion is 100 kPa for the stiffer layer, and for the softer layer it is C2 is 35 kPa. Okay, the saturated unit weight of the stiffer and the softer layer is 20 and 18 kilonewton respectively. So gamma saturated 1 is equal to 20 kilonewton per meter cube, and gamma saturated 2 is equal to 18 kilonewton per meter cube. So the unit weight of the stiffer layer above the water table. So this part, okay, the unit weight of this part, suppose it is gamma 1, it is, how much it is? It is 18 kilonewton per meter cube. 18 kilonewton per meter cube. Determine the bearing capacity of the top layer. Now we are asked to have been asked to find out the bearing capacity of this layer. Okay, we have been asked to find out the bearing capacity for the top layer. The unit weight of the water is 10 kilometer cube. We need to use that method, Mayer and Hanna method. Vertical load is acting at the center of foundation. That means there will be no inclination factor, and neglect the soil compressibility effect. That means no compressibility factor should be incorporated. Okay, that means CQ and C gamma, all these are not needed. So now for the top layer, okay, need to find out the bearing capacity only for the top layer. So for the top layer, that is QT. Last one was QB for the bottom layer. This one is for the top layer. So for QT, let me write down the equation for the bearing capacity. That is C1 NCA1 SCA1 plus gamma. Let it be like, let me denote it by Q. Okay, so Q into NQ1 is Q1. Okay, plus the third term half into gamma 1 B gamma 1 S gamma 1. In the last case, we used all the parameters of the second layer. See C2, NC2, SC2, NQ2, SQ2. Okay, because in the last question we are asked to find out the bearing capacity for the bottom layer. In this case, we are asked to find out the bearing capacity for the top layer. So in this case, we will use all the parameters for the top layer. So since this one is totally clay, this one is a cohesive soil totally, so there will no phi. So phi is equal to 0. So for phi is equal to 0 degree, NC or NC1 will be equal to 5.14 and NQ1 will be equal to 1 and N gamma will be equal to 0. Like in the previous case, so it was also a cohesive soil. The second layer is also cohesive soil. That's why in the last sum, we use the same bearing capacity factors. Okay, 5.14, 1 and 0. So this one N gamma is 0. This one is N gamma. N gamma. So that means this part will be 0. Only this part and this part will remain. So Qt, now if we incorporate the shape factor over here and all the bearing capacity factors into this equation, if we incorporate all those things, it will be like 5.14. 5.14 is the so what is so 5.14 is the bearing capacity factor NC1. So 5.14 into C1, we have the C1 into the shape factor SC. What is SC? For a rectangular footing, since this is a rectangular footing, SC is equal to 1 plus 0.2 B by L. Okay. And what is Q? Q is the surcharge. Okay. Surcharge at depth df. In the last case, we found out the surcharge acting on the top of the bottom layer. Okay. And since now we need to find out the bearing capacity of the top layer, we need to find out the surcharge acting at the depth df. That means over here. So what will be the surcharge acting over here? So 0.5. So that means the unit weight of the soil above the groundwater table, 0.5 into gamma 1. That is the unit weight of the soil above the groundwater table, 0.5 into gamma 1 plus gamma submerged into this part. So what is this part? This part is df minus zero point 0.5. So this part is df, that is from the base, from the top of the groundwater table to the base of the foundation. What is the thickness? It is df minus the groundwater table depth, that is 0.5. So df is equal to 1 and the groundwater table depth is 0.5. So if we subtract 0.5 from 1, we will get the thickness of this portion. So it is 0.5 meter. So what will be the value of Q? So it will be like 0.5, the thickness of the of this portion from the surface to the groundwater table. This portion is 0.5 into unit weight is 18. So 0.5 into 18 plus this portion. So this portion is 0.5 as I have explained. So 0.5 into what is the submerged unit weight? The saturated, we know it is 20. So 20 minus 10, that is 10. So 0.5 into 20 minus 10, that is 10. Okay. So Q, and what is the value of NQ is equal to 1 and SQ is also 1. So now if we solve this, we know the value of B. B is the breadth of the footing, that is 2 meter, and this one is the L, the length of the footing is 4 meter. So 2 meter, that is 2 meter, and this one is 4. If we put all the values and we know the value of C1, what is C1? C1 is 100 kPa. If we put all the values in this equation, we will get Qt is equal to 580 kilonewton per meter square. Okay, so this is the bearing capacity of the top layer. If you have any problem regarding this, if you have any doubt regarding this problem, please let me know. Let me know if you have understood this problem or not, or else I will proceed to the third part. In the third part, we need to find out the bearing capacity of the whole system. Okay, this one I found out the bearing capacity of the top layer. You will understand in the third part why we are doing this separately, and in the third part we need to find out the bearing capacity of the whole system, of the two layered system together. So please let me know if you have any doubts regarding this problem. Shall I proceed to the next problem? Okay, so let me proceed to the next problem. In this problem, all the information is similar. All the information is similar. You need to find out the ultimate bearing capacity of the two layered soil system. See, it is mentioned over here, two layered soil system. And it is also mentioned over here the adhesion along the vertical shear plane in the top of stiffer layer, which is 0.92 times the cohesion of the top layer. See in this diagram, what is the vertical shear plane? It is this plane, and the cohesion along this part is CA, which is alpha into C1. Alpha is given, is mentioned over here. The alpha value is mentioned over here. It is 0.92, and so C1 is also mentioned over here. It is 100 kPa. Okay. So now for the two layered system, and since this is a rectangular footing, we need to use the Meharov and Hanna 1978 approach, because we need to combine both the layers. Okay. So what was the equation? This was the equation. Okay, this was the equation for the, this one is valid for the strip footing only, and in the current question it is a rectangular footing, so there will be just some shape factors. Okay, some shape factors will be incorporated into this equation, nothing else. And since in the current question there is only cohesive soil, so there will be no phi, so this part will be 0. Okay, because in the current question it is, we are considering only cohesive soil. Okay, so tan 0 means 0, so tan phi 1, so tan 0 means 0. Okay, so this part will be 0. Okay, so now let us solve this problem. So now the ultimate bearing capacity for the two layered soil system QU is equal to QB. You know what is QB? It is the bearing capacity of the bottom layer plus the shape factors. The shape factor is 1 plus B by L, and now the other parts. The other parts, this part and this part, 1 plus B by L into 2 CAH by B minus of gamma 1H. Now this equation, okay, I am not considering the third part. I am not considering the third part. Okay, this part, because phi is equal to 0 in this case. Okay, okay, let me write it down once. QB plus 1 plus V by L to CA by H by B minus of gamma 1 H plus this part, gamma 1 H square, the shape factors, that is 1 plus B by L into 1 plus 2 df by H into Ks tan phi 1 by B. Since this part is equal to 0, phi 1 is equal to 0 degree, so tan phi 1 is also will also be 0, so that means this portion will be 0. We are not considering this portion. So the ultimate bearing capacity of the two layered soil system will only be this for cohesive soil. Okay, so now we know the value of QB. We have already determined in this question. We determined the value of QB. It is 217. So QB, so QU is equal to 217 plus 217 plus 1 plus V by L, 1 plus 2 by 4 into 2 CA by CAH by B, 2 into CA. So what is CA? CA is equal to alpha into C1, right? CA is equal to alpha into C1. The adhesion along the vertical plane in the top layer is 0.92 times the cohesion of the top layer. So alpha is 0.92, alpha is equal to 0.92, and C1 is 100 kPa. So 0.92 into 100. Okay, 0.92 into 100 into H. So what is H? H is the thickness of this layer. See, H is the thickness of this part. Let me see in this diagram. H is the thickness of this part from the base of the footing to the top of the second layer. So the df is 1 and the depth of the top layer is, so the df is 1 up to the, from the depth of the foundation is 1 meter, and the thickness of the top layer is 1.5 meters. So this thickness will be 1.5 minus 1, that is 0.5 meter. So H, so H is equal to 0.5. 2 into CA, 2 into CA into H, 2 into CA into H by B. So 2 into CA into H by B. So what is B? B is 2 meter. Okay. And minus of minus gamma 1 into H. What is the unit weight? Uh, Gamma 1 into H. Okay. Okay, so gamma no into h. Okay, we will consider the submerged unit since the footing is submerged. Okay, since the footing is submerged, so we will consider the submerged unit of the top layer. So the saturated unit of the top layer is 20 kilonewton per meter cube. So if we subtract the unit of the water from this saturated unit, that is submerged unit is equal to gamma sat minus gamma w. So that means 20 minus 10. Okay, so minus gamma 1 into h. Gamma 1 is equal to 10, that is 10 into h. What is the value of h? That is the thickness of the from the base of the foundation to the top of the second layer, it is 0.5. Now if you solve this, okay, equation, you will get the value 281 kilonewton per meter square. Okay, now one thing you should remember, that is the equation, okay, the ultimate bearing capacity of the two layered soil system. Okay, this whole thing should be less than the bearing capacity of the top layer. That means this whole thing, okay, whole thing should be less than qt, the bearing capacity of the top layer. Okay, now we will check. So this is the value of qu. So let me write it down. So qu, the bearing capacity of the two layered system, what is it? It is 281 kilonewton per meter square. 281 kilonewton per meter square. Okay, so what is qb? That is the bearing capacity of the bottom layer. It is 217 kilonewton per meter square. And what is the key value of qt? The value of qt is 580 kilonewton per meter square. Okay, so you see it is satisfied over here. The qu is less than qt. Okay, so if you have any problem regarding this question, you can tell me if you have any doubts. And please follow the course, the video lectures of the Professor Deb, to understand this more clearly. I have explained all the steps in details. In this way, you will follow. In this way, if you follow the problem, if you solve the problem, you will be able to do it easily. So please let me know if you have any problem, if you have any doubt regarding this problem, the two layered soil system.
No, sir, any doubt.
Okay. So now let us proceed to the final question. So in the final question, we'll also use the same method. So let me read out the question. Here, in instead of the rectangular footing like we used in the previous question, we will use here in this question. It is mentioned that find out the we need to find out the ultimate bearing capacity of the two layered soil system for a strip footing. So earlier it was a rectangular footing. Now in this case it is a strip footing. Okay. So now, so in that means there will be no shape factor. That means the shape factors will be different in this case. So now, and all the other things will be similar. It is similar to the previous question only. Okay. So difference is the shape factor. So now let me draw it. So a strip footing of width 3 meter. So a strip footing of width 3 meter is founded at a depth of 1 meter in stiffer clay. The thickness of the stiffer layer is 1.5 meter. Suppose this is the stiffer layer, the thickness is 1.5 meter. The water table is at a depth of 0.5 meter from the ground level. Zero point 0.5 meter. A softer clay layer is located below the stiffer layer. So a softer layer is over here. The undent cohesion of the stiffer and softer, like in the previous problems, it is same. So C1 is equal to 100 kPa and C2 is equal to 35 kPa respectively. The saturated unit weight of the stiffer and softer layer is 20 and 18 kilonewton per meter cube. Gamma sat1 is equal to 20 kilonewton per meter cube and gamma sat2 is equal to 18 kilonewton per meter cube. The unit weight of the stiffer layer above the water table, that means the unit weight of this part is 18 kilonewton per meter cube. Determine the ultimate bearing capacity of the two layered soil system. The unit weight of the water is 10 kilonewton meter meter cube. We need to use Meyeroff and Hanna 1978 approach. And the vertical load is acting at the center of the foundation, so there will be no inclination factor. We need not consider the inclination factor since the load is acting vertically, and neglect the soil compressibility effect. So that means there is no need to incorporate the CC, CQ and C gamma factors. The adhesion along the vertical shear plane, I have shown you what is vertical shear plane, and along you know what is adhesion now. You know what is adhesion along the vertical shear plane. I have shown you alpha into C1. So alpha is 9.92 like in the previous case. So only difference is here it is a strip footing. Okay. So let me write down the ultimate bearing capacity equation for the strip footing for a two-layered soil system. It is QB plus, I have already written over here, you see this one, QB plus 2 CAH by B gamma 1 H square 1 plus 2 DF by H, okay, minus of into, sorry, there no minus, into KS 10 phi 1 by B minus of gamma 1 into H, okay. So I will write it down it once again, and in this case it is also a clay, it is the layer, the soil is also clay, so phi is equal to 0, and so the ks 10 phi term will also be 0, this whole term, uh, because you know 10 phi, so phi equal to 0, that means 10 phi will also be equal to 0. So now let me write it down. Q is equal to QB 2 CAH, the bearing capacity, so 2 CAH by B plus gamma 1 into H. And in this case also it will be less than QT, that is the bearing capacity of the top layer. This one is the bearing capacity of the bottom layer, as I have shown you in the earlier problems. So now let us find out the value of QB and QT in this case separately. So QB, so what is QB? QB is the bearing capacity of the bottom layer, which is C2 NC2 plus Q2 NQ2. Okay. So Q2 and NQ2. Okay. So you know the value of C2. What is the cohesion of the second layer? The cohesion of the second layer is 35 kPa, the softer layer. So 35 into NC2. This one is clay. So that means NC In case of clay soil, the NC is always equal to 5.214 and NQ is equal to 1 and N gamma is equal to 0. Okay, so NC is equal to 5.14 plus Q. What is the surcharge on top of the bottom layer? What is the surcharge on top of the bottom layer? It is 0.5 into the unit weight of this layer above the groundwater table and the submerged unit weight into the thickness of this part from the top of the groundwater table to the top of the bottom layer. Okay, so the total depth of the top layer, the total thickness of the top layer is 1.5 meter and the depth of the groundwater table from the ground surface is 0.5 meter. So that means the thickness, this part, only this part is 1.5 minus zero point 0.5. So 1 meter. Only this part is 1 meter. Okay, 1 meter. So that means the surcharge acting on top of the bottom layer is 0.5, that is the thickness of this portion, into gamma, that is 18 above the groundwater table, plus the thickness, this thickness, that is 1 meter, 1 meter into the unit weight, the submerged unit weight. 1 meter is this part. And what is the submerged unit weight? The gamma set is 20 and unit weight of water is 10. Okay, so this one. And NQ2, what is NQ2? It is 1. Fine. So now if you solve this, you will get QB is equal to 199 kilonewton per meter square. It is the bearing capacity of the bottom layer. Okay. So now we need to find out if this value, I have not calculated everything. So we will also find out whether this part is less than Qt or not, because this is the limit. It must be less than Qt. So we also need to find out Qt, that is the bearing capacity of the top layer. So what is the bearing capacity of top layer? That is C1 NC1 plus Q1 NQ1. Okay. So what is the value of C1? C1 is 100 kPa. And what is the value of NC1? It is 5.14. And what is the value of Q1? That is the surcharge acting at depth df, that is over here. What is the surcharge acting at this level? It is C. The depth of footing is 1 meter and the depth of groundwater table is 0.5 meter. So that means this depth will be 0.5 meter. Okay, df minus 0.5. So what is the surcharge acting at the depth df? It is 0.5 into 18 plus 0.5 into the submerged unit weight. Okay, so it is 0.5 into 18 plus 0.5 into the submerged unit weight. So what is the saturated? 20 minus 10. 20 minus 10. Okay, and what is the value of NQ1? The value of NQ1 is 1, because this is completely cohesive soil. So NQ is 1. Now if you calculate this, you will get QT is equal to 528 kilonewton per meter square. Okay, so now you know the value of QB and QT. So now you need to calculate QU, that is the ultimate bearing capacity of the two layered system. So what is QU? QU is equal to QB plus 2CAH by B, 2CH by B plus gamma 1 into H. Sorry, it is minus gamma 1 into H. So minus gamma 1 into h. Okay. So now QB. What is QB? QB is 199 kilonewton per meter square. 199 plus 2 CAH. 2 into CA. What is CA? CA is equal to alpha into C1. Okay. Alpha is equal to 0.92. It is mentioned in the question. See, 0.92 times the addition along the vertical shear plane in the top stiffer layer is 0.92 times the cohesion of the top layer. So cohesion of the top layer is 100 kPa C1 and alpha is equal to 9.92. So 0.92 and C1 is equal to 100 kPa into H. What is the value of H? H is the depth from the base of the foundation to the top of the bottom layer, this part. We know the value of df, which is 1 meter. If we subtract df from the thickness of the top layer, that is 1.5 meter, we will get the value of h. So h is equal to df minus 1.5 meter. So df, sorry, it is actually reverse. Let me write it over here. So what is h? H is actually the thickness of the top layer, that is 1.5 minus df. So 1.5 minus df, what is the value of df? Df is equal to 1 meter. So h will be 0.5 meter. So h is equal to 0.5 meter. And what is the breadth of the foundation? The breadth is 3 meter. So 3 meter. So 3 minus gamma 1 into h. So gamma 1, what is gamma 1? This is total, this is a saturated soil. Okay. So the top layer is this portion of the top layer is saturated, so we need to consider the saturated unit of this soil. So gamma sat1 is 20, so 20 minus 10. So 20 minus 10 and into h. What is h? H is equal to 0.5. So you know all the values, you know alpha, this one is alpha, this one is C1. If you calculate this equation, you will get QU is equal to 225 kilonewton per meter square. Okay. So now you see QU is equal to 225 kilonewton per meter square. So let me write it down once again. QU, that is the ultimate bearing capacity of the two layered soil system, is equal to 225 kilonewton per meter square. Okay. And it should be less than QT. And what is QT? QT we got 528 kilonewton per meter square. 528 kilonewton per meter square. Okay. And QB, that is the bearing capacity of the bottom layer. Bearing capacity of the bottom layer is 199 kilonewton per meter square. Okay. So this is the answer. So it is satisfied that it is less than the bearing capacity of the top layer. And so the bearing capacity of the two layered soil system is 225 kilonewton per meter square. Okay, so if you have any problem regarding this question, you may tell me now. This is the last problem of this session. Please let me know if you have any doubts or not. Please let me know if you have any doubts or not.
Yes.
Yes, tell me if you have any doubts or not.
No, sir. No, sir.
Okay, have you understood everything which I did today?
Okay, sir.
Okay, okay. So see you in the next session. That is after 1 week. Okay. So good night. I am ending this session.
Thank you, sir.
Okay, you may leave.